Hello Pantherae, my friends, and today I will show you how to compute this particular integral. So, the key how to do that is to write the partial fractions in a complex domain, which I will show you it's very easy to do. First, I would address that more comprehensive or more skillful reader, for them it would be easier to compute this with an identity with a gamma function. I would strongly recommend to do this by the way, or to use complex analysis. Here I will not be using complex analysis, just basic complex numbers, basics in complex numbers. What are the numbers which null this polynomial, which are the roots of this polynomial? So there are we can write them on the Gauss's real and imaginary plane, a ground plane, and this is -1, which is e to the power pi I divided by 2n. This is the first root which lies on the unit circle over there, and if I put minus sign here, doesn't matter. There is another solution which is this is, we call it omega 1. Call it this solution will be omega 1. I'm sorry, omega 0, we will call it omega 0, and there is another solution, omega 0 hat with I component, imaginary component, switch to the -1. So the key standpoint here is to proceed further. The next solution, there are many solutions. A couple multiples of these are 2 pi k divided by 2n, and these solutions form all solutions roots of this polynomial. They are located on like this polyhedron or poly something, I don't know the name for it, polyeder, polysite, this, and this angle is the same, and so we have these solutions and we can write partial fractions for them. Let's write it like this. Partial fractions, what are, there is a summation, there should be a summation from k is equal to 1, and I will not sum up to 2n, there are 2n actually, these points, but I will 0, I will sum up only to n minus 1. There are this is n roots, but this polynomial has 2n solutions, so we should add another solution which is complex conjugate of this. So there is x minus omega k, and this is omega k, and this is x minus omega k conjugate, and there should be a number c k and ck and dk. Yes, there are two numbers, and there is dx. How to determine these numbers? It's very easy to do, because if I will multiply this by for example this x minus omega k term, I will and take the limit, I will get the ck is exactly 1 over x 2n plus 1 divided by x minus omega k in the limit. But as you may know, this is 0 and this is 0, so in the limit this is L'Hopital's rule, so this is 2n x to the power of 2n minus 1, and this is this. So if I multiply it with x, and there is 2 to the power 2n, x to the power 2n, which is minus 1, so this is minus x over 2n evaluated at x is equal to omega k, or in the second case omega k conjugate. So there should be minus 1 over 2n and ck. Oh, this I should rewrite this. There is minus 1 over 2n minus infinity to infinity, and there should be dx and omega k, x minus omega k plus omega k conjugate divided by x minus omega k conjugate. Then I will write it on like the same line to the same denominator. So this is minus 1 over 2 over n. I should write it on the different row. Yes, minus 1 over 2n times an integral minus infinity to infinity dx summation from k is equal to 0 to n minus 1 to x times this and this. So there should be x squared minus omega k plus omega k conjugate x plus omega k conjugate, and there is x times this plus x times this, which is x times omega k plus omega k conjugate minus omega k omega k minus this, which and minus this, so this is minus 2 times omega k conjugate. Now if you look closely in this, you will see, oh, this is omega k with plus omega k conjugate is e to the power minus pi I 2n minus 2 pi k over 2n. There should be I also. If you multiply these two, omega k and conjugate and omega k, you will get 1. Omega k and omega k conjugate is equal to 1. And if you sum them up, you should get cosine, because there is e to the power something times I and e to the power minus something, the same something times I. So omega k plus omega k conjugate is equal to 2 times cosine of pi over 2n plus pi k. I will cancel out these 2's over 2n. So there should be like this is minus 1 over 2n, an integral minus infinity to infinity 2 times x cosine of something. I will denote this number as 2 times capital CK, so this is 2 times x capital CK divided by minus 2, because there is minus 2, divided by x squared minus 2x c capital CK minus plus 1. So this and there should be also a summation from k is equal to 0 to n minus 1 and dx, the differential. This is equal to what? As you can see clearly here, there are two parts. One is, I can rewrite this as minus 1 over n, from minus infinity to infinity, and there I can write 2x, and there is like x 2 times cosine k x minus 1. I should minus this x minus cosine k, and this should be minus 2, so there is minus 2 times sine k. Sk is the same as this, but there is sine, divided by because cosine squared plus sine squared is 1, so this is minus 2, and there is x squared minus 2x cosine k plus 1 dx, and also I forgot the summation again. Interestingly enough, this is very easy to compute, because now this part is the derivative of this with this ck, so there is an equal sign. 2 is this, 2 times x minus 2 times ck, which is derivative of the denominator, so this is minus 1 over 2n ck, first summation from k is equal to 0 to n minus 1, ck times logarithm of x squared minus 2x ck plus 1. And the second term is minus, and minus is plus, plus 2. 2 will cancel, so there is plus sk divided by 2n times integral from minus, I told you that n 2 cancels, so there is sk divided by n. There should be a summation from k is equal to 0 to n minus 1, some integral minus infinity to infinity, and there should be differential divided by x squared minus 2x ck plus 1. And I will left as an exercise to a reader that this term will vanish. You can prove it yourself. This term will vanish. So this is 0. Evaluate it from minus infinity to infinity. You have to take it as a limit as r approaches to infinity minus r and r plus infinity. This term will vanish, so I will deal only with this term. So this term is by the formula I showed you last time. This should be this is 2 divided by square root of minus determinant, which is here 4 ck squared minus 4. So the square root of determinant is there should be 4 times sine k squared times what there should, oh, I'm sorry, this should be squared, because there is squared, so this is squared and this is not squared. Arcus tangent of the derivative of this, which is x minus 2x minus 2 ck, but the 2 will cancel out with this, so this is sk. Sk you can show is positive for sk to a k is equal to 0 to n minus n corresponds to points on the upper half plane in the complex plane of all zeros. So this should be, so for the summation from k is equal to 0 to n minus 1, 1 over n I will put over there. Sk will cancel with this, 2 will cancel with this, so there is just sk. Arcus tangent from minus infinity to infinity, and this is pi over 2 minus pi over 2, which is pi. It's just pi, I will put pi over there. So you have to compute just this summation. This summation is very easy to compute. You can use methods, for example, from complex analysis, but just basic complex numbers, because if you write sine k as an imaginary part of e to the power I times this argument, which is over there, pi over 2n, plus pi ki over n. I'm sorry, there should be no 2's in there, because there are no 2's, so there is pi k over n just, so there is pi ki over n, and this summation, I will just sum these terms, so this should be pi over n imaginary. Part of this is constant of k, so there is exponential I pi over 2n, and there is geometric series. The formula is 1 minus, and there are n minus 1 terms, so there should be n, so there is e to the power of n this, so this is pi I over 1 minus the quotient, which is pi over n times I, so this is e to the power pi I over n. And if you this can be like multiply together, this is minus 1, so this is 2, so there is 2 over, this is 2 actually, so this is pi over n times 2, and I will multiply whole numerator and denominator with e to the minus this, so there is 1, so there is 1, so this is e, an imaginary part of e to the power of minus this, minus e pi over 2n, minus, and there is pi I over n minus pi I, mean minus, so this is plus I pi over n, and this, if you multiply, this is what? This is minus 2 times I times sine, yes? This should be like minus sine of pi n pi over 2n. So the 2's will cancel out, and the final result, if you take the imaginary part, is 2 pi over 2n times sine of pi over 2n, yes. And this is the final result. I will leave to the reader how to compute this example, which is more, it might be more complicated, but you can compute the same integral for 2n over n. This is a rational number, and this is a rational number, and then from continuity of this, it's straightforward to show that this result holds true for all real values positive greater than 1, that the integral of minus infinity to infinity dx x to the power alpha plus 1, where alpha is greater than 1, is equal to 2 pi over alpha times sine pi over alpha. This comes from continuity of this correspondence, and you can show this. So thank you for watching. This is the derivation of this particular integral with imaginary parts, and I think this is not so complicated, and I hope you enjoyed it, this series, and maybe next time. So Panther and goodbye.